Okay, so today we are in the last section of Chapter 1, Section 9. It begins on page 52. We're talking about the problem-solving plan. And I think somebody in 7th grade asked about this yesterday. And I said, we're going to be talking about the problem-solving plan tomorrow. So why do we use this QFUOS? And if you have been at St. John's, I think you know the phrase. Can you say it? It is?
Queen Fiona uses outhouse seats.
Right. So let's show that phrase. Queen Fiona uses outhouse seats. It's just a little acronym for remembering the 5 steps to the problem-solving plan. So years ago, when working with the 5-step plan, I was working with a group of students who are currently sophomores in college. And we said, well, what really does the 5-step plan come down to? Because it's kind of hard to just memorize a 5-step plan. This plan was put together by a very smart mathematician named George Polya from Stanford, a Nobel laureate. And we talk about him when we're addressing the problem of the month here. So they came up with the fact that there are some important letters that help them remember the 5-step plan for each step. And the important letters were these, Q, F, U, O, S. And so they said, well, what phrase could we come up with to remember that? And I think Shrek must have come out with one of the Shrek movies or something. And so they came up with Queen Fiona uses outhouse seat. So that's what this is a little outhouse seat, which has never been really used, but was decorated so that we could remember the 5-step plan. You could use this if it's made to put on a 5-gallon bucket. And then you could use it if you were camping, and you could carry the bucket and dispose of your waste somewhere very easily. I know it's not a pleasant thought for everybody. Okay. So let's talk about this. Okay, Q stands for what is the question? And in algebra, or as we create the equation, that's our variable. That's what is unknown. We're trying to find that. So it is the variable. F stands for what are the facts. And we're talking about numbers that are needed to solve the problem. Not adjectives about the problem, numbers that are needed to solve. U stands for,
Unnecessary.
Everyone say it, unnecessary facts, basically, unnecessary numbers. Don't use them. In the real world, we are presented with tons of information, and we have to zero in on the important facts when solving problems. And we have to be able to screen out those things we don't need, okay? And O stands for what are the?
Operations.
Everyone say it. Operations. And so when we were talking about translating words to math earlier this year, we were looking for, we made a whole big list of words that represent the 4 basic operations. Can someone give us one of those words? Give me a word that represents, and raise your hand, addition. What word might we hear?
Sum.
Sum. Find the sum. Give me one more that represents addition.
Plus.
Plus. Okay, give me one more that's used in more general at home or at play or something like that. What might you hear? And. Okay. The team was made up of, 5 defenders and 11. That doesn't sound like the right numbers, but okay.
How many more?
How many more? Good. Okay, and so we know that those things mean addition. Give me a word that means multiplication. You might come across in a real world. Times something. Product. Or double. Triple the numbers or something. Okay, so those are what we discussed, and you can go back and look in your notes for those big lists that we created for all those operations. S stands for solve. And when we say solve and check. You always want to check your work. It's at this step that we write the algebraic equation. Algebraic simply means it has a variable, as we have said. So the goal of the problem-solving plan is to take a real-world situation and write one equation that has a variable for your unknown in it, right? And it has all the important facts. If we can write that equation, we now can solve for the unknown. one given that we didn't even write down is that the very first thing you have to do is read the problem. And it is true that there are math students who attempt to solve problems without even reading it. And so usually when you call me over for help during this kind of real world problem section, the first thing I ask is, did you read it? I know it seems ridiculous. You would think, I would assume you did, right? But I have found in many cases people just haven't even read it slowly. You've got to be reading it, and you have to be really aggressive and go for it. Sometimes I think people shy away. There's a paragraph and you shy away and you step back from it. But no, St. John students need to be aggressive. Read it, start jotting down some notes as you read it, and then maybe you're going to be reading it a second time after you get kind of a little understanding of what's happening. Sometimes it does take 2 readings, right, to really pull out what you need, because you don't even know the question until you've read it through once. So please be aggressive and make sure you carefully read things. And for some of you, that means kind of out loud. You might in the classroom be whispering it to yourself, but it helps you to really slow it that much that you're reading it out loud. Let's try using the problem-solving plan for this problem. So go ahead and jot it down. Okay, so we're going to together walk through the 5-step plan. And as I was just saying, the answer right now doesn't matter to me. What really matters, 8 out of 10 points, is can you create an equation that shows this story in one equation? Then the little answer is 2 out of 10 points. I mean, it's nice that you get it, but really what I want to see is, can you create this equation, this algebraic equation? So we can jot down our little acronym. Queen Fiona uses outhouse seats. Start looking for these things. We read the question nice and slowly. I think we've read it more than once, and when you write it down, it gives you time to really think. So what is, somebody tell me in just a small number of words, what is the question here? Jensen? Okay, so trains in 1 hour. That's the question. So what letter might be good, Jensen, to represent this? T for trains, why not? Okay. T. There's our variable. We want to see that in the equation that we create. And now we need the facts. What facts are needed to answer this, Miles?
There's 5 cars.
Per 5 cars per what?
Per train.
Okay, there's a rate. 5 cars per train.
And then each car holds 4 passengers.
So how can I write that? 4 what? 4 people per
1
car. So there's another rate. I have 2 different unit forms in each of those. And so that's interesting. Any other facts? Cooper?
900 people to ride a lawnmower.
900 people in 1 hour, right? In 1 hour. Interesting. 900 total people in 1 hour ride all these trains, however many. The question is how many trains in 1 hour up there? And we know that 900 people travel in 1 hour, so we're just trying to figure. Is there any other fact that we need? There. No other fact? We have them all? Okay, then are there any unnecessary facts? That was our next question. Any unnecessary facts, which again are numbers. It's not about adjectives. Like, what would be an adjective here? Like an amusement park or something. That's not really what we're worried about. We're worried about using numbers that are unnecessary. So are there any?
No.
No, and so that's nice. We don't have to worry. Just strike that out. And now operations. What did we say is the operation that's used 99% of the time when you have a rate? It is, Luca? Multiplication. Multiplication is probably happening here because we have all these rates, okay? And so now I don't want to just solve it. I don't want to know how many trains, honestly. I want to see an equation that shows this whole story. And when you create it, it should contain these 3 facts, right? And it should contain that variable. There's 4 things for sure that should be contained in this. And it's an equation. So what else will it have? An equal sign. So some equal sign is there. So who wants to give me one side of the equal sign? What will be on one side for sure? Sophia?
The equation itself.
One side of the equation will have what?
An operation.
Okay, one side will have an operation. Can anybody give me actually an expression that would be on one side? Mark?
You do 5 divided by 4 times 900.
Okay, so he said, so that's interesting, but Matthew?
So you use 4 times 5.
Okay, if you're going to use this, then I want you to carry your units. So everyone is talking about the 5 and the 4 right now. So if I put 5 cars per train, then why are you multiplying that to 4, Matthew?
Because 4 passengers in 1 car.
Passengers per car. Now let's just take a look at this. If I was to multiply these, and just forget about the numbers for a second, just look at the words. Look at the units that are being used here. If I multiply this, which units are going to disappear? Everyone?
Car.
Everyone?
Car.
Cars. I have cars over cars. Cars over car. That unit, that's a multiplicative inverse, isn't it? Those become 1, so they disappear. Car over car disappears. So is that good? Do we want to get cars to disappear?
Yes.
Because ultimately the answer is supposed to be what?
Trains.
How many trains? So we still have trains visible there, so that's good. Okay? And so now we have, it looks like we would multiply the top and we'd have 20 passengers per train. Is there anything else we would need to do with that information, 20 passengers per train, in order to find how many trains in an hour? Luca?
So you would do numbers like that, 900 divided by 20.
Okay, so how does that fit onto this right side of the equation? Are you putting 900 on the right side of the equation or on the left? Again, we're trying to advance our algebraic thinking. You are right, we ultimately will do that, but I want one equation that shows a story. So that's, we need to make that happen too. So really, once we find out how many passengers are, or how do we find out how many passengers? Do we already know how many passengers travel?
Yes.
So is that some big total? No, it's not 20. How many passengers travel in an hour? Isn't that some big total? We know that 900 passengers travel. So isn't that going to be something, where would that appear? Since it is a big total, where would that appear? I need a new hand. Left side, good. I hear it. 900 people total in 1 hour. Okay, so there's something else we need then. We have 900 people total, and it depends on the number of cars per train, the number of passengers per car, and what else? Take a look at your, we already have how many people per train, don't we? We have 20 people per train, and what else do we need?
We need the number of trains.
We need the number of trains. So do we have that?
No.
Where would that go then? Or how would you use it, the number of trains?
You would use the variable to do
The variable's t?
T times 900.
Actually, isn't it the number of trains? T number of trains, right?
Yes.
T number of trains. Now, take a look at what we have on the right, just at the units. If we put T number of trains on the right, and we were to multiply that whole thing together, what is our other multiplicative inverse? What else is going to cancel out? Do you see it? Trains. We have trains over trains. And what unit are we actually ending up with? Actually, we use two different, is passengers the same thing as people?
Yes.
So that's one thing that we, I guess, should have used the same word for. They are the same thing. So we could change this word to people, I suppose. And now we have the number of people should equal the number of people. And now we are ready to solve. So you've actually created the algebraic equation. I know this was hard. It looks like this, 900 people. If we take away too many letters, we'll just call them 900 people, equals 5 cars per train times 4 people per car times the number of trains, right? Again, I'm using the whole word train because we used the variable t. So I don't want it to be confusing. And as Lucas said, if we multiply 5 times 4, you all said it was 20. So let's just get rid of the units. Do we all agree that we end up with people on both sides now?
Yes.
Okay, so if we just look at the numbers, 900 equals 20 times what?
T.
T. So Luca, what did you say we would end up doing in the?
900 divided by 20.
So the operation we see right here is 20 times t. So what will we do to both sides?
Divide.
Divide by 20. Good. Is exactly what you were thinking. And that gives us the number of trains. 10 over 10 is 1.
45.
And so what is the number of trains?
45.
45. For those who have done the math. There you go, 45. Which is the least important piece of this. The most important piece of this is, can you write this big equation? You see how challenging that is? That is not an easy thing for a student to do. And a 5th grade student would never, very rarely, be able to do something like this. What does a 5th grade student do?
That's most high.
Don't they just go all over the page and put stuff all over the page and then try to bring it together? Right? So when I say we're after doing it 7th grade style, this is 7th grade style, where we take a big problem and attempt to create this beautiful equation. And it's not easy. So we're going to work on that in the next couple of days. We just were doing what's called unit analysis. We were looking at the words to tell whether our answer was correct. And if the answer is correct, then the units that you're left with should be the correct units. So if it is correct, the answer needs to have the correct units. But we need to work with words. The words are the units. And this is not as easy for you as working with numbers, but with practice it becomes more comfortable. Having words over words, it's an interesting thing. We're going to try this one additional problem together. So go ahead and take it down. So we are going to, again, read it carefully, attack it, and try to create one equation that shows this story. So, we say Queen Fiona uses outhouse seats. And the question, what is the question? And the question is somebody else. Sophia.
Explain how checking is.
So, okay, well, and what would the question be in here?
Explain why Matt thinks that, explain why one of the friends thinks Matt spent $16.
Why 16, I guess, right? So we don't even have a variable, it seems like, does it? We're checking whether it's true that he spent 16 or not. Give me a fact, Alex.
Each hot dog is $2, please.
Okay, so hot dog, $2 per hot dog. There's a rate. And give me another fact. Claire, give me another fact. Okay, he ate 3 hot dogs. 3 hot dogs. And what? Another fact. Another fact. Somebody else. What other facts do we have here? Sean, do you see another fact?
$10 for a ticket.
Okay, so everyone is writing their numeric equation that shows this real world situation. And Cooper, do you have one?
I have a question.
Okay?
2 times 3
So she has
What is it?
2
times 3
per hot dog. I'm just gonna use H for that, times 3 hot dogs.
And then
Okay.
I kind of have this parentheses.
Around that?
Yeah.
Okay, so this is the hot dog thing.
And then I have plus 10, because that was plus.
Plus, and she did $10 for the ticket. You could even say times 1 ticket, right? And there's the other thing, and then what finishes it?
And then I have
Equals what?
equals 116.
16. We actually have that given. I'm going to put a question mark there because the whole goal was to check, is this true? So the question mark tells me that's what we're checking. Is this true? Okay. When we multiply, in the first expression she gave us, the hot dogs cancel, and we end up with dollars, don't we? How many dollars are there? $6. And when we multiply here, the tickets disappear, and we end up with dollars again, and we get how many dollars? 10. And so is it true that $6 plus $10 equals $16?
Yes.
Yes, we have checked it, and it is true. Okay, beautiful. Not easy. It's a lot of work that goes into this, but beautiful. You will have very few problems to do because you can see how much work goes into them. It doesn't mean that the whole assignment is really shorter. It means that you're given the time to really aggressively use your 5-step plan to do this process, okay? And here's your assignment.